Hello everyone, welcome to our presentation and to our Honorable Professor, Dr. Jaime Honra. Good morning, sir. This presentation is part of the requirements for the completion of Master Course MA210, Advanced Thermodynamics. The group member are as follows: Engineer Nelson Compay, yours truly, and Engineer Edren Paul Disales. Our topic is about modeling and analysis of absorption refrigeration system with lithium bromide water as part of substance using ASPEN software. Let me give you a short recall about absorption refrigeration system. From the definition, it is a refrigeration system without a compressor, as you can see from the diagram, and rather no external work to compress the refrigerant. In this case, the work of pump to increase the refrigerant pressure from low pressure region to high pressure region is relatively low, therefore, it's considerably negligible. A substitute to the compressor is the absorber and generator, this one, that produces a solution of refrigerant, and the refrigerant is superheated by the external heat. So let's analyze further the process flow of this diagram, and I'm going to start at point 1, where in low pressure strong solution from absorber will be pumped to a high pressure generator, wherein heat is added to separate part of water from the solution in vapor form to act as a refrigerant that goes to point 3, and remaining weak solution will be flowing at the point 2, going through the throttling valve to reduce its pressure and going back to the absorber. From point 3, point 4, and point 5 will be the same process as the compression refrigeration system, wherein heat is rejected from a condenser to transform the refrigerant vapor form to its liquid form, and then it passed to expansion valve to reduce its pressure and temperature. Then it goes to the evaporator to produce a cooling effect or cooling load and change the refrigerant from liquid to vapor state. Then it mixes again to the absorber to form a strong solution, and the cycle repeats. On this presentation, we are going to find a solution to the problem, which state that we need to create a lithium bromide water absorption refrigeration system model with generator temperature of 100 degrees Celsius, condensing temperature of 40 degrees Celsius, and evaporator temperature of 10 degrees Celsius, and absorber temperature of 30 degrees Celsius using ASPEN Plus software. So we are going to start now using ASPEN software. So the first step is to define all the properties that we are going to use throughout the process. On component tab, we are going to define our working fluid. On this case, it's water and lithium bromide. After that, we need to select the electrolyte wizard option to add all the possible reaction, including the water dissociation reaction. Next is to define the property method. In this case, it's already pre-selected by ASPEN software based on the first input we made, and it selected the ELEC and RTL. This one means electrolyte non-random to liquid. After that, the ASPEN will retrieve all components parameters needed from its data bank. So after defining all the properties, we are now ready to create a model for our simulation. So basically, ASPEN software has its own built-in predefined blocks, which we are going to use to create a model for absorption refrigeration system, the same on the problem stated earlier. The finished model should be look like this. After creating the model, we are now defining all operating parameters for each equipment and stream. For the input, this stream is the property of working fluid entering to the pump, which has a 30 degrees Celsius temperature and 1.138 kilopascal pressure. This is equivalent to the evaporator saturation pressure and a mass flow rate of 1 kilogram per second of lithium bromide water strong solution. Next is the pump, which has a discharge pressure of 7.409 kilopascal, that is equivalent to the condenser saturation pressure. The next one is the generator. This is set, wherein heat is added to increase the solution temperature up to 100 degrees Celsius. I put 0 kilopascal here to signify that there is no pressure drop on the equipment. For throttling valve, we define the outlet pressure, the same with the condenser pressure, which is 1.138 kilopascal. Then it follows by the absorber, wherein heat is rejected to maintain its operating temperature to 30 degrees Celsius and 0 kilopascal as pressure drop. Next is the condenser, which reject heat to maintain 40 degrees Celsius temperature and change the vapor to liquid water with a 0 pressure drop. Then it follows by an expansion valve to reduce the pressure of the refrigerant to 1.138 kilopascal and subsequently its temperature. Lastly, the evaporator, which produces a cooling effect or cooling load and maintain a temperature of 10 degrees Celsius and change the refrigerant from liquid to a water vapor. After defining all the operating parameters, we are now ready for the simulation. So this is the screenshot of the graphical report created in ASPEN. It shows all the parameters on each equipment and stream. The most important one is the heat added on the generator and the heat load on the evaporator, which we are going to use to evaluate the system coefficient of performance or COP. Another important point to notice is the work of the pump, which is very low. That's why it's considerably negligible in COP evaluation. This is the summary report. In here, we can see that our model has a COP of 0.6476, which is far from COP of a reversible cycle, which is 1.7706. So overall, this plant has an efficiency of 37%. These are the ASPEN generated detailed report for each equipment and stream, which we can use for the material and equipment selection and further detailed design of the plant, which is not part of this presentation. Let's end my presentation. Thank you for listening. The next presenter is Engineer Adrian Paul Disales, in which he are going to discuss how to improve the COP of the lithium bromide water absorption refrigeration system.